So I'll start off by giving us a little bit of an overview of what's been posted last night on the website, and then I will proceed to get into the lecture. We have a pretty nice lecture for the day because it's confined to probability and random variables, random processes, and then we'll start the applications of that and eventually end up with quantization noise in A to D conversion, and that will kind of lead us down the path to the homework problems that we have on this set. We, of course, have the project running in the background, so in the meantime, I'm going to get into that. Just trying to get things out of the way here that I'm not used to having on my screen since I'm running a Zoom. So, taking a look at the website, you can see that I've posted, just to be on top of everything, I've posted both set 5 and 6. I've also posted the hints. They're on lock just because I was in a hurry last night to get everything up. 6 comes after 5, obviously, but I'm just trying to look ahead, especially to the week of Thanksgiving, which, being that we're only on November 6th, it's hard to think about the very end of the month, but things will move along quickly, so I want us to be prepared for all of that. So we'll look at 5 here in a moment. Project 1T, or Project 1, which we were looking at last time, is definitely up and running. I reposted it, and we went through problems 1 and 2 in quite a bit of detail last week in class. It's on the video as well. The third problem on DSP components, phase accumulators, numerically controlled oscillators, and a few other components that I've developed and have been developing, is sort of on hold for right now. I think it's likely that I don't want to really add it with all the other work we have to do. I'm continuing to push on it, and I'll just roll down to this part of the screen in the project to explain what's going on with all of that. This is the component that I wanted to focus on in problem 3. But I've also been working on an upgrade to Scikit DSP-COM in the synchronization module. This has been going on for over a year. I just haven't been able to get all the components put together, actually translating several of them from Julia back to Python. But the plan has been to provide this for the synchronization module in Scikit DSP-COM. So these other components that I was going to base the project on are related to that. They're related to phase lock loops and automatic frequency control, or AFC, tracking loops. It's possible that I will turn this into the final project because I've been working on a notebook which is going to go along with the push to GitHub. But just stand by on that. Just pretend that problem 3 is basically turned off for the time being. I really just want you to focus on 1, 2, 4, 5, and 5 has got multiple parts to it. So let's go back over to the homework, and we'll just review through some dates while we're looking at the homework. This homework set is due on November 15th, and if you look at the bottom of this, you can see that I'm announcing formally the take-home exam, which takes place at the end of the week before Thanksgiving, and then terminates on Wednesday with your submitting the take-home exam on the 27th. So this is absolutely going to move forward. This will be a more straightforward exam than what you had in exam 1. It will be a take-home exam, of course, but this will come out on the web and may come out earlier than Friday. I'm just saying no later than Friday, November 22nd. What's specific about that, though, is if we go back over here and move down and look at set number 6, it's due on Friday, November 22nd. And the hints, like I said, are already up there. This is based on Chapter 5, which we haven't gotten to yet, but we will move into lecture-wise starting next week is my plan. And what that covers is what Chapter 5 does is in problem set number 6. And Chapter 4 and 5 together constitute the main material for Exam 2. So we need to make all that stuff happen. And if you're worried, don't get too worried, because we're talking about the whole month of November before we actually get to that. And you have to perform on the exam close to the end of the month. So it's going to unfold step by step, but I'm just sort of laying the groundwork for that here and letting you know what's out there. The project is also due at about the same time, but as long as you're working some on both homework and on project, you should be in good shape. I would be working hard on Project 1 right now and start looking at problem set number 5 sometime, probably over the weekend or something like that, maybe late at the end of the week on Friday. Just see what's been done there and how you're going to be able to get into it based on today's lecture. So with that said, I'm going to jump over and get ready to start the lecture formally here. And I'm going to expand the full screen here in my PDF viewer and just get going. So we're discussing discrete time random signals, and in order to get there, we're going to first give a quick review from what you would have had in probability and stats, ECE 3610. If I'm remembering the numbers correctly, I think that's the right number. So the reason why we want to do random signals is that we need to be able to analyze quantization behavior and also noise processes from other sources that will show up in our DSP systems. This is totally valid for all of DSP, but it's especially valid for communication systems. The first communications theory class, Com 1, doesn't really get into the noise aspects except in the Appendix A at the very end of looking at noise figure and how white Gaussian noise models enter the scene there. But everything else that you do with systems like comm systems or audio processing, noise is always a factor. So the modeling that comes from what we're going to go through in today's lecture is valuable stuff. So to get into the quick review of probability, it's not really going to be something that you're going to be solving problems in very much. There is a problem on set number 5, the very first problem, which we'll bounce into when that time approaches. We'll also see that all of this is covered in the Jupyter Notebook for Chapter 4 really well, and I intend to go jumping into there eventually too. So what is the foundations of probability? It's considering an experiment that has outcomes chi sub I, and chi sub I is just a notation for all the possible outcomes that could come from running a random experiment. And we generally view those as elements in a space known as the sample space. And going back to tracing your memory back into probability, the simple example that I like to think about is flipping a coin or rolling a die. there the sample space is discrete, so it has, like in the case of a coin, a head or a tail. Those are the outcomes. And if it's a die, it's the 6 faces on the die. But if you want to think of maybe playing a board game that has a spinner in it, for example, where you spin something and see what angle the spinner is at after you do that event, that would be an example where the sample space is continuous, because it can take on any number of angle values between 0 and 360, and that's a sample space that corresponds to the real line, in the sense that it has an uncountable infinity of outcomes. All of that can be managed with probability theory. So another part of the review here is that if we look at a subset of the sample space, that could be A or B, and then A or B could be composed of elementary outcomes or from the sample space. So it could be it's a set, though. Fundamentally, it might be A might correspond to just the single element chi1, and then B could be 1, 3, and 5. And in this particular case, A is a subset of B. So subsets of the sample space, as talked about in the example of A and B, formally in mathematics, make up a sigma field in field theory from mathematics, advanced mathematics. But the foundation that we need to know is events, which are subsets of the sample space, are of particular importance, because that's when we can assign probability. So we say the sample space is the entire space, so it's called the certain event. And anytime the random experiment runs, the certain event occurs, and the probability of it occurring is 1. If you have an empty set, that's called the impossible event. That means you have a set composed of none of the elementary outcomes from the experiment, so we can assign a probability of 0 to that. But anything in between, if we contain elements from the sample space, then we have some probability assigned to it. So, and that's the measure of the likelihood of that event occurring, and that's called probability. In modern probability theory, it's based on 3 axioms. The probability an event is always greater than or equal to 0 if we're talking about the probability of the certain event, and that's, again, just S. That equals 1, and then we have the third axiom. It has to do with the set intersection of A and B, which is either written in logic theory as A times B, or in mathematical set theory notation, we would use the intersect sign. And if that is empty for A and B, in other words, there's no elements in common between A and B, then we have the third axiom that tells us that the sum of the events in A and B, which is also written using the union symbol, the U there, combining the sets together, A and B, that is the probability of A plus the probability of B. And you might remember this from Venn diagrams in probability theory, but it's just saying if you have 2 events that are mutually exclusive, they don't contain any elements in common, then the probability of the union of those 2 events is the sum of their probabilities. So going back to what I had in the picture up here, if I'm thinking of a die which has got the discrete space of 6 faces, we could say that event A would be the probability of face 1 occurring, and on a fair die that would be 1/6. Event B looks like face 1, 3, and 5, so those would be the odd numbered faces of the die. And if you were rolling a die, you would say that the probability of getting an odd numbered face is 1/2. And you'd deduce that by saying that, well, the probability of any one face is 1/6, so the probability of getting face 1 or face 3 or face 5, which is like the union of the events corresponding to the elementary outcomes, that would be the sum of those probabilities. 1/6 plus 1/6 plus 1/6 is 3/6 or 1/2. We also have axiom 3 extending to the union of n mutually exclusive events, and then it's just the sum of those probabilities. Now, another type of event is the intersection, like we were just talking about, probability of A and B, and that's written also in this third notation is used a lot, where you say put a comma between the events. So with probability, we also have conditional probability. Given two events A and B, the probability of A given B is written as the probability of A and B over the probability of B. So we might think of today being a snow delay day. We could say something like the outcome of it snowing, well, a random experiment of what's the days like, what's the probability that it's going to snow out, and then we could further extend that with another event, that it snows and we get enough snow to cancel early classes. So that could be thought of as a conditional probability. We're now conditioning upon the fact that it has snowed, which would be B, and then A would refer to having a delayed start or some sort of a cancellation. So if we narrow our scope down in our probability to say that the day it did snow out, and then that if it does snow, what's the probability that we cancel? That's a conditional probability we could define. And if you take conditioning in one direction, A given B or B given A, you have similar definitions, and that also brings about the concept of Bayes' rule, where you can condition from one direction or the other using Bayes' rule right here. Do we have specific need of that in this class? Not really strongly, but I just put it in for the review. Then we also have the theorem of total probability, which says that if you have n mutually exclusive sets or events, and they're such that they cover over the entire sample space, then for an arbitrary set B or event B, you can write it as an expansion of the conditional probabilities times the so-called marginal probability of the event AI occurring. That could be another way of getting at the probability of getting the odd faces or the even faces or something in the die experiment. Okay, so I'm just going to move beyond that. Again, that's not super important in what there are applications upcoming. I'm just reviewing. Independence is an important property, though. We'd say two events are statistically independent, and then we say if and only if probability of A and B is equal to the product of probability of A times probability of B. And the if and only if means that if this is showable, given the problem construction, that allows you to say they're statistically independent. And then the if part says that if they're independent, then this mathematical relationship is true. So it's a powerful statement. It's generally used in our applications when we're just approximating things. We're going to have a noise source A and a noise source B, let's say, and we're wanting to know what happens if we consider a random process that has got noise from two different sources in it. We generally would assume that they're independent of one another, and then that gives us more powerful, a means to get more powerful conclusions, and that we would not be able to get unless we made that independence assumption. And it's a reasonable assumption in most cases, but other cases would not be true. Like in a sensor array application, you might have two microphones that are picking up a signal from different geometrical locations, and the noise field is present, background noise, people talking, whatever. You might just model that as just one noise source emitting sound into the audio field, and both sensors are going to pick up copies of that, and in that case it would not be fair to say that they're independent, because there is some correlation between the two as they're received by the individual sensors. Okay, now we're going to move on to random variables, which is the next level up from basic probability. And I'm going to guess that most of you liked random variables over just plain probability. To me, as an engineer, random variables just seem a lot more hands-on oriented, rather than thinking of the story problem that you usually end up with when you're doing a discrete or when you're doing a pure probability problem. So here, the idea of the random variable is it takes the sample space S, and rather than just thinking of those elementary outcomes, the chi denotations, and mapping them into some random variable. And so here it's shown as a random variable X is considered as the locations where the elementary outcomes map out onto the real line. And if there's just a finite number of elementary outcomes, as kind of depicted here, you would just have probability mapped onto the real line at discrete points. A real fundamental example of that would be taking the die problem in the 6 faces and just putting the face values into a random variable X, and say that the probability of landing at 1 would be 1/6, the probability of landing at 2 would be 1/6, because we're just mapping the outcomes from our experiment as face values, but now putting them on the real number axes. In the notation of random variables, a notation that I tend to like from a book that I used to teach random processes out of is a boldface X would denote a random variable, and then it's math italic. So this is the boldface right here, and this is the math italic font. So the boldface X denotes the random variable, and the italic X denotes values that it may take on. So the values that it may take on are values that sit on the real number line, and they're mapped through the random variable definition itself as this boldface X, given that it's, say, chi2 or chi1 or chi3. Now, not all books go with that notation, so the alternate notation that a lot of other books like to use is, when they're talking about a random variable, they'll use a capital X to denote the random variable, and then the lowercase x, just like we have up here, the math font, is the value that it takes on. So, however, you can get even lazier than that, and that tends to be what the book does and the way some of the homework problems are written. It's just lowercase x, and you have to decide on the writing and the language and the problem. Are we talking about the values that it takes on, or the fact that it is the random variable itself? So we'll see some of that when we look at the problems. For right now, I'm trying to be more full in the notes just because I want you to be clear on the difference between the random variable and the values they take on. So what is the first characterization of a random variable that you remember from review would be the so-called cumulative distribution function, or CDF. So in the notation of our book, it would be something like probability of random variable x at value little x, and that corresponds to a set of chi values such that x of chi is less than or equal to little x. So in the way you probably remember being taught random variables, it's the probability that random variable x is less than or equal to little x. So I like that better, that's clearer, but I'm just letting you know that in the book they've defined it more or less as it is on the left in this expression. There is an appendix on probability and random variables in the back at the end of the book, so if you want to get more clear on the notation, you can take a look at that. So what are probability properties of the CDF? When you're sitting at little x equals minus infinity, the probability of that is 0. If you take little x and stretch it all the way out to infinity, the probability of that is 1. And a way of kind of visualizing that is if you're sitting over here and you're looking at all the probability that's been mapped up until that point, from minus infinity up to that point. If there's been no probability mapped onto the real line up to that point, the total probability is 0. So that's why when you set x equal to minus infinity, nothing has gotten up mapped onto the real line from the random variable definition. Whereas if you go way out over here and then want to look at what's been mapped out from minus infinity up to that point, as this edge goes out to infinity right there, everything's mapped out onto the real line at that point. By the time you get to positive infinity, everything's on the real line from the mapping at the random variable definition, and you get 1 for the probability of that, because that's now the certain event. A property of the CDF is it's right continuous, so as x goes to x plus, it's the same as p of x is 0. So it's continuous from the right. It has a discrete behavior to the left of that. So you might remember that if this is x and we're looking at the CDF for a discrete random variable, it's going to consist of jumps in it. So it might go along like this, and then it will jump up to some value like that. Trying to pick the right colors here. So if this was faces on the die, the picture's not drawn quite right. Probability has already been mapped out before x1. If it was the faces of the die, nothing would be mapped out till I got to x1. But if we're just looking along the CDF over some interval of little x, we're just going to see jumps like this occurring that are right continuous. So I've got the parenthesis at the end of the intervals, meaning that it's an open interval. It doesn't actually have a value at x1 because it jumps up to the next higher level at that point. So another way of looking at the CDF is to say that it's a non-decreasing function because it's got the property that as you increase x, you're always accumulating more probability, and the probability of an elementary outcome, which is the set corresponding to just one element in the sample space, is always greater than or equal to 0. So you're always going to be either increasing the probability of the CDF by some non-negative value as x gets bigger. So it's non-decreasing. As an engineer, I think most of us prefer the density function over the CDF. The CDF is the accumulated probability as x runs from minus to plus infinity, and that's the non-decreasing function. But I think we tend to like the density function better because that's more of a physical interpretation, that we've got probability spread over the real line, probability density, I mean, and so we get at that by differentiating the CDF. So we've got, if it's a discrete probability situation, then we've got point masses sitting along the line. As we integrate through those point masses, which are like delta functions in math modeling, then we accumulate more probability. Or if we think of a uniformly distributed situation, then you just got a uniform density of probability per unit length of the x-axis. Think of that as density. Then we get these properties. Density is always greater than or equal to 0, which makes sense. Can't have negative probability. You integrate the entire density, you get 1. You've integrated the entire mapping onto the real line. And then if we're interested in the probability of being on a half-open interval, because of the discrete, because of the right continuous property, we have less than here and less than or equal to here. That's just integrating the interval from, say, x1 to x2 to get the probability associated with landing in that interval of the PDF. And I'll take a really simple example where it's continuous. Suppose we have a continuous uniformly distributed random variable. It would have a height of 1 over t, and the t on and 0 to t on the x-axis is where it exists. So if we're looking at integrating that entire density, we get 1, and if we look at just an interval, let's see, starting to write t. I wanted to write x, so we integrate over that interval, and that gets us the probability of being on that interval, which in this case that's going to be what that probability is, right? The width of the interval times the density, which is 1 over t. We can have joint random variables where we have more than one random variable defined, and unfortunately that sounds confusing, but unfortunately that is the way modeling works. We don't have just one random variable in our life. We end up having multiples, and the reason why that is we'll see with random processes. We might have an input x that's a noisy signal, and then we send it through a system, and that system produces output y. So now we'll have two random variables present. We might also model the input as being composed of signal s which would be a random variable, plus noise n, which would also be another random variable, or actually random process. So we have signal plus noise at the input, and then we process it in some way, and we get signal and noise at the output as a result of that processing operation, like a filter or something. So if you're wanting to consider the joint random variables, where we might have x and y as input and output, or just two different random variables that we have defined in our model, we have to have the joint CDF given to us in the problem statement, or modeled with assumptions, and this is where the independence assumption can come into play. I'll just say that if we didn't know how to model this any other way, and we just said x and y are independent, then we could just write this as the probability of the product of the probability of the CDFs, or it would be the product of the PDFs if we went down into that part of our definitions. And those are the types of things that we're very apt to use in our modeling, where we're going to assume independence or uncorrelatedness. Haven't gotten to that yet, but so we can have conditional CDFs, conditional PDFs. The conditional PDFs are what I've got defined here. They just follow the exact same form as the conditional probability ideas. You have a joint PDF on x and y divided by the marginal PDF on x, and that's the PDF on y given x is present. And then the reverse of that, and then Bayes' rule for joint PDFs. If we have independent random variables, like I was just saying, then the joint CDF is the product of the marginal PDFs, or the PDFs on x and y alone, and the CDFs the same way. This right here is a favorite in modeling that we'd like to be able to use at various places in what follows, and we're going to be using it for, say, quantization noise, for example. Since I'm sitting down and I've got the ability to have my own drink here at home, I'm just drinking something to keep my throat from getting too dry. You can only see me if you're watching this on Zoom right now. Otherwise, you're just going to see the general standard recording that I make with just the screen. So statistical averages, that's probably our most valuable review. Part of the review here is that we take measurements, and we take measurements to characterize things about our system. So the first and fundamental one is taking the mean, and that would be denoted here in the notes and in the book as m sub x, so the mean on x, and then our operator that we have in random variable theory is the expectation operator, and so expectation of x is the mean on x, and given that we have the PDF on x, we can get that by integrating x times the PDF on x, and that's from mechanics. That would be the first moment. Of huge importance in the types of things you work in the homework problems is this property right here, fundamental theorem of expectation. The very first homework problem on set number 5 weighs heavily on this, and I'm going to explain it a little bit on the next page, but fundamental theorem of expectation says that if we have some function of the random variable x and we want to find the mean on that function of x, we can just simply plug that function into our expectation operator in place of x itself. And in one of the books I taught probability and random variable theory from at the undergraduate, 361 or 3610, I mean, this was also termed the rule of the unconscious statistician, which I thought was a good statement to make. It's like if you don't know what else to do and you're just thinking, without thinking too hard, you just say, I want to find the mean. I'll just say that this function of random variable x has a mean that's just given by plugging that function into the expectation operator. So we'll take an example of that here. We're given here the definition of the variance. The variance is the expected value of x minus mx quantity squared. That's the definition. It's called the second central moment, is another name for it. It's called central because we're taking x and subtracting the mean from it, and it's the second moment because we're taking the quantity squared. So how can we just think about probability theory and fundamental theorem of expectation? So the first thing I would do is I would just take the expectation operator here and we expand this out. Just multiply it out. So we're going to have random variable x squared minus 2 times random variable x mx, and then we're going to have mx squared. And the expectation operator is also linear in the sense that if we can expand out what we're finding the expected value of, we don't have to do anything more than just move on this using linearity. So this is going to be the expected value of x squared minus 2mx, because that's not a function of the random variable, that's a constant. Expected value of x plus just mx squared. The expected value of a constant is just that constant. So we have 3 terms over here on the right, and then if I reduce that down, I'm going to get expected value of x squared minus mx squared. Now I'm making some assumptions here. I'm saying that that's just going to be the mean on x. So I have 2mx times mx minus 2mx squared, but then I have mx squared at the bottom. So I'm netting out of that that quantity. So I get the mean square value, which is expected value of x squared minus the squared mean, which is mx squared. And that's the linearity operator. Why am I going to dwell on this? Let me just jump over for a moment since it's convenient here. Let's just jump over and look at the very first homework problem. So in this very first homework problem, I'm giving you a random variable x, saying it's uniform on minus 2 to 2, and another random variable y that's uniform on the interval 0 to 4, and I'm saying assume that x and y are independent. I want you to form the random variable z, which is a function of, so I can write on this, function of x and y and some constants. What you're going to want to do to characterize this random variable is you're going to want to, first off, I've asked you to find the mean on z, and to find the mean on z, you're just going to fundamental theorem of expectation. So you're going to say I'm going to take the expected value of z on the left-hand side, and then I'm going to wrap the expected value around these terms on the right, and then let it operate on x, let it operate on minus 2y, and then it operate on 2. So you'll be able to write an expression for the mean on z in terms of the individual expected values of these terms. Likewise, you can do the same thing for the variance. You would plug in this whole thing, subtract the mean from it, and then square it out, and then again work term by term. But there's a trick to working term by term to make life a little bit easier here that I propose talking about later. I would say right now, if you'd asked me to do it later, I would consider doing it later in the class, but I don't think anybody's watching on Zoom right now to ask a question of me. But if you are, let me know that you're watching, because I'd like to know that. I can't tell if anybody's watching right now. Maybe I can. I don't think I can. I don't think anybody's on right now. At any rate, remember I'm doing this because I want to get a lecture done for the day, and then I can produce the video and then push it to YouTube. So if I'm talking to myself, I'm okay with that for right now. At any rate, going back over, well, let's look at this problem a little bit more. So you calculate the mean and variance for this new random variable z, and then I'm going to have you simulate each of the random variables in using NumPy's rand function and look at it through a histogram, and also look at it as the mean and variance, and we'll look at that in Python here eventually. And then you'll do the histogram at the end. You'll do the histogram on the function z and use the hist function. I'm doing this as a review, but I'm also doing it because some of these things enter into some other problems, some things that may happen in project problems, and things that you might confront in work down the road with some of the modeling that you could end up being involved with. So moving on here, if random variables x and y are uncorrelated, this is another definition, then the expected value of x times y is the product of the expected values. And furthermore, if x or y has zero mean, then we would know that either this term or this second term would be equal to 0. So then that allows us to say that uncorrelated random variables, in the case of one of them being zero mean or both, means that they're also orthogonal. And orthogonal is just a way of thinking of in an abstract vector space that x and y are like vectors in an abstract vector space, and if two vectors are orthogonal, the dot product, which would, in this case would be the expected value of x times y, is equal to 0. So that's just another fallout from that. And this idea is pretty common in signal modeling because generally the signal and noise at the input to a system are uncorrelated, and the noise is generally of zero mean. So this idea holds in that sort of modeling. Okay, a couple of popular PDFs that we'll be using here. Uniform, as I've already talked about, but formally this is the definition. Uniform on the interval a to b just says that the height of the density is 1 over v minus a, and it's 0 otherwise. So drawing a picture of it, it looks, as you can see down here, just a rectangular pulse shape, only it's defined on the random variable axis x. The notation that people would use in the literature, books, and so on would be capital U to mean uniform on an interval a comma b. The second popular PDF is Gaussian or normal, and that has two parameters that control it. one being its mean and the second being its variance. And this is the standard bell-shaped PDF that you're used to seeing. And it's an e to the minus x squared kind of a function with a normalization out in front. This normalization out in front is just ensuring that when we integrate this function, we'll get 1. When the variance is small, the bell is compressed about the mean, and when the variance is large, it's spread out about the mean. The area underneath the bell has got a tail that's known, it can be written in terms of what's called the Gaussian Q function, and the Gaussian Q function is defined here as this integral. This is not a closed form integration, it's a special function. So to actually get that tail probability, you have to use some sort of an engine that's available in software such as Python or MATLAB, Julia, Mathematica, etc. This is an approximation to the Q function, and then I listed a few values over here in a table. Probably the most important thing about this is just to notice that as x gets bigger and bigger, the tail area gets smaller and smaller, and it shrinks down very rapidly once you're out here to 4 standard deviations away from the mean. The tail is shrinking on the order very rapidly in orders of magnitude. We'll be able to jump in and do all these things in Python in a little bit. Or maybe I should go take a look at that since I think I've got it running here already. This will make sure I can get on the right page. So we're following down in Chapter 4, Jupyter Notebook. We went through and looked at these reviews or introductions to project problems 1 and 2 last time. So now we're at this section of the notebook, and I'm going to close that so I have more space. And the way we do a lot of things in Python is through modules that are imported into our environment. So, for example, we have 2 modules that we use a lot, NumPy, and then we have various modules from SciPy. And when we have NumPy, we already have some stats capability through the sub-package called random. But if we want to get really sophisticated, we can load from SciPy the stats sub-package. And just to give you an idea, here I've imported SciPy stats as stats, and if I just type tab in there, you can see all of the things that are available in SciPy stats. So most of these have to do with PDFs, either continuous or discrete, that you might want to work with, more exotic ones than the basic ones we're going to work with. And there's also object-oriented calculations for generating PDFs and then taking measurements on them, like the tail probabilities and so on and so forth. For us, though, we don't really need the power of the stats package. We can get by with NumPy, numpy.random. When we have already imported all of NumPy at the very top of our notebook, then in order to get access to what's in the random package, we have to go inside of random itself. And if I go inside of random itself, I'll see it's got a lot of PDFs and other calculation means. As I scroll down here, we have things that we're going to want to take advantage of. Now, I think mean is already brought in outside of that. Let's just go up above here. I've imported NumPy already, so let me just type mean. And yeah, mean is already built in without having to go inside of random, and variance is also in there, as well as standard deviation. So those are three core functions. I think we also will use covariance in one of the homework problems. So let's see. Yeah. Covariance. Those are the things we'll be looking at. So if I wanted to generate some uniform random distributions, I know that the rand function, for example, can generate a multidimensional random set of variates. But if I just fill in one value, D0, that will be the number of variates I want to generate in one dimension. So I'm going to generate 100,000 variates. And rand, by definition, is uniform on this interval, 0 to 1. And if I subtract 1/2 from it, I'll make it uniform from minus 1/2 to plus 1/2. So here I've generated a collection of random variates, x1, x1a, x3, and x2. And they're out there right now, and I could go do things with them. Let's just test out some ideas, though. If we make it uniform on the interval minus 1/2 to plus 1/2, which is rand on 0, 1 shifted by minus 1/2, then what do we expect for the mean of x1? It's going to be 0. I mean, it's about as close to 0 as we can get with only 100,000 samples thrown in there. If I put in 1a, or no, I put in x3, that is just the straight up rand. So its mean value should sit where? At about 1/2. So there we have that. We'll take on some of these other things here. Well, I talked myself into it since I'm here. I'll just say, okay, so if we want to take a look at the density function, we can use the hist function, which has got a lot of options in it. I'm doing Shift-Tab, and you can see all the options available in hist. Fundamentally, though, it produces a plot, a histogram plot right in place, and an option that I'm kind of fond of is well, the number of bins is the second argument, but the third argument that I enter, I don't have to enter any of these because they have default values, but if I go ahead and declare an argument that I would like to enter value for, I can just say density, and it defaults to a false value, but if I set it equal to true, then I'm going to normalize my PDF, or my histogram, to look like a PDF. And there it is with 50 bins. Wait a minute, that's not the right PDF. I wanted to go with X1. So that's when it's got 100,000 samples in it. I don't know what X had in it. It was not a random variates example, though. That's pretty close to 1, burning from minus 1/2 to 1/2. And if I put in X1A, which here was just another synthesis of 100,000 samples, I should have the same thing, and it's uniform. But now if I put in, say, let's put in X2, see if we can reason out what that is. And this is hovering around things that you're doing in homework problem number 1. Okay, so I can reason out what's going on here. This is uniform on 0 and 1, so this multiplying times 5 is going to make it uniform on 0 to 5, which means the height of it's going to be 0.2, so that its area remains 1, and then I'm shifting it by 3. So instead of going from 0 to 5, it goes now from 3 to 8, just as a result of that transformation. I could do variance calculations. I could do covariance between two random variables. So here I did an example of the covariance between x1 and x2. We're not quite to understanding covariance, but let me just sort of make you think about it. If I look at the covariance between x1a and x1 and x1a, I'm getting it a more or less a finite number that's 0.08, which has to do with the variance along the diagonal of this matrix, and then the off diagonal is a very small number because they're uncorrelated approximately. They're actually independent according to the way the random numbers are generated here in Python. The two different sequences are drawn from the same pool, but they're independent realizations, each one of them. So if I take two different collections of 100,000 samples, they're independent of each other. And that's the model, at least. They're uncorrelated for sure, and we're going to see that that's what this term is. If I was to do something more fundamental, like just take the product of x1 times x1a, I'm getting a really small number. It's because they're uncorrelated from each other, and they're of zero mean, so I'm getting a very small number. If I put in that, I get the variance, because the squared mean is 0, so that's what that 0.083 is, which is a number you've seen before back in probability and random variables. You know that the variance of a uniform random variable is delta, the width of the uniform random variable, divided by 12. And that's what I'm demonstrating right here, that the variance numerically is 0.083 with some digits random beyond that, and then compare that to 1/12. It's basically the same number. The width of my uniform distribution is 1 unit wide, and I know the variance is delta over 12. Here I generated using RAND and then RAND N 10,000 samples. So I created a uniform distribution that runs on 0 and 1, and I created a Gaussian distribution with variance 1. And I think, I haven't looked at what this code actually produces. Oops, I didn't run this cell first. I just had it produce PDFs of the uniform from 0 to 1, and then of the Gaussian PDF approximation. They're not of the same variance, though, because the uniform is a variance of 1/12, and the Gaussian, by definition, is a variance of 1, and that's what this number down here is telling you. This is the 1/12 that we've seen for the uniform. Regardless of what interval, where the interval is centered, it's still a width 1, and then the Gaussian is, by definition, 1. Of course, if I was to modify this, multiplied by square root of 2, the random variance is the same as the variance being multiplied by 1 or by 2. So now the spread on the Gaussian is greater, and we'll see that in the estimate of the variance, it's now 2. That's another theorem developed from the fundamental theorem of expectation. So if you scale a random variable by a, the variance will become a squared times the variance of the random variable. And that's what I did here, which is why I put in square root of 2, so that when I square root of 2, it becomes 2, and that means the variance on this new random variable is going to be the variance of the underlying random variance times the square of that. So that was 2 times 1. Okay, enough on that for now. We're going to go off into the exciting new topic here, random processes. And they're connected to the random variables, which are connected to the probability. So as you can see, though, I've gotten more or less focused on random variables up to this point. They're more relevant to what we want to do in this class, and they're more relevantly connected to random processes. So here's the definition then. A random process is a family or ensemble of functions of both time, it could be space, but we're going to use time-oriented random processes, and elementary outcomes from the underlying sample space. So we could have time t, or we could have time n for the discrete time. So in this class, our focus is discrete time random processes, but we'll get them by sampling continuous time random processes in a radio receiver or in a audio sensor array processing application. So what happens with the random process is each elementary outcome that's inside the sample space is assigned to a time function rather than just a value on the x-axis, as in the random variable case. It's now an entire sequence. So it'll be x of n due to elementary outcome chi sub I. So it's a sequence of values. So if we're looking at the discrete time random process definition, it would be the idea of an ensemble of sequences. And here's the depiction that I like a lot. Try to make that fit on the page. We have this underlying sample space, that's the probability part, and then it elevates it up to the random process part by saying each one of those elementary outcomes produces another waveform or sequence. And the number of elementary outcomes can, of course, be uncountable infinity in the continuous random variable or random process sense. So we'll have an infinite number of waveforms in our ensemble. So I like to think of this ensemble as not just being the 3 waveforms you see here, but this arrow extends up to say that there's waveforms above this and there's waveforms below this. There's an infinite number of waveforms sitting right here, all stacked up on top of one another, so you can visualize them. So when you're looking at a random process, you can interpret it in 4 fundamental ways that are related. First, you can say it's a family of time functions. So you just have to consider it as this massive ensemble of waveforms. Second, a single time function. So in that case, you would say, I don't want to be bogged down, or I don't need to be bogged down with all the functions. I just want to consider it as one time function. You could consider it as a random variable by just slicing it vertically, which is what this dashed box here is doing. So just slice down at one time index through all of the sample functions of the ensemble, and now you've just got a random variable, and those are the various values that the random variable takes on at that index n. And of course, the last one is just focusing in on a single sample value. So you might say, I'm just going to pick one sample function and one time value, and just going to say that's it. It's that value. It's some negative number at that particular index. These interpretations seem initially, if you, for the first time viewer of random processes, it seems kind of overwhelming that you have to think in this large sense of having this ensemble that contains an infinite number of waveforms. Now, this idea was something that was created by man to model randomness in nature or electronically generated by some other signal coming at us. So, is it a necessity that we have a random process model? No. Is it convenient and useful? Yes. So it's put up as a useful modeling tool to try to understand and represent things that our system is going to have to deal with. So the ensemble just gives us lots of flexibility in how we characterize things, and then how we consider the interaction with a system and a random process. How does the book like to do random processes in the notation? My preference would be, if I can get this thing to work right, boldface x, just like it's a random variable. If it's a boldface x, now we put square bracket n to say that it's a waveform or a sequence, and that we could say is the whole ensemble. The book tends to say that I'm just going to write it as an ordinary sequence, little x of n, and then let it be understood if it's a random process or not. If it's just a random variable, it's just what we get when we slice down vertically at index n. So all the interpretations come about from the discussion that goes with it. So I'm switching the notations from here on in to be more consistent with the way the book would have it. I'm not going to use the boldface anymore, but just want you to know that in this case we're talking about a random process, x of n. So we're thinking of it as an ensemble of functions. And we have to think widely in the sense that it's got an infinite height of sample functions vertically, and each sample function starts at minus infinity and goes to plus infinity. So there's a lot of information out there in an ensemble. So the mean on the random process x would just be the expected value of the random process x. I'm standing up right now, so if you're watching me on the video, you're seeing me moving away from the camera, but I'm just tired of sitting. So we just write here the expected value of x. We don't have an answer for that because we haven't given a definition of the random process yet, but the thing to take away from this, though, is that in general, the mean of a random process is a function of time index n. Likewise, if we plug in the definition of the variance of a random process, we get something that is also a function of time. However, if a random process is stationary, then everything is a constant. Both the mean is a constant, regardless of where n is, and the variance is a constant. And we're heading in that direction. We're going to actually be aligning ourselves with what are called wide-sense stationary processes, which don't have fully all the properties of stationary, but they have the core basics, and they're a lot more practical to deal with in real systems. So modeling things is a wide sense stationary process. So a new definition that comes in here, mean and variance we had for random variables, but now we can enter into, we had covariance in a random variable, now we're going to have something called autocorrelation, and that's a function of two arguments, m or n and m, and it's the expected value of sequence x times itself conjugated but at index m. So what we're thinking of doing now is taking two waveforms, or the same waveform in itself, but shifting one with respect to the other and visualizing what is the correlation, or a better way of thinking it in terms of our picture over here. I'm going to go through and try to delete some of these things. Just have to use my finger to get that to go. So a better way of thinking of it is when we're doing the autocorrelation function, we're taking this ensemble sampled at this value of n, and then we're taking from the ensemble this one, call that m. So we could think of it, this is x at m, and that's x at n, so that's sampling vertically through the ensemble at index n and at m, and we're looking at finding the expected value of the product of x at n times x at m. So we're saying we have two different random variables now. They're actually drawn from the same random process, but we're sampling at different time indices, and that's how we define the autocorrelation. And the conjugate is in there because if we have a complex random process, we just want to be able to handle that too. And in software-defined radio, complex random processes are common. But we're not really going to be dealing with that in what we're going to do in this class, but the book gets you prepared for that. The autocovariance sequence is a variation on the autocorrelation, except that for each of the sample function, or each of the vertical slices you take through the sample functions, you subtract the mean at that index, and that gets you the autocovariance. And the covariance and the autocorrelation are related, kind of like the mean square and the variance are related. The autocorrelation function minus the product of the means at n and m with the conjugate thrown in there is equal to the autocovariance. And in particular, if we have n and m equal, then the autocovariance is just the variance on the process itself. And I know in the beginning, and I know that we don't do much more than the beginning in this introduction for this class, you come away thinking there sure are a lot of things to remember, little definitions of this and that. We're not going very deep into this. You do have a few homework problems, but then we'll just use some high-level properties from here on out. So the detailed random process-oriented things occur in really just one problem of the homework set number 5. And I'll just quickly jump and look at that. If I can get that page right. Yeah. You get into random processes a bit in this text problem, 298. But if you're looking to get help on that immediately, you can just jump right into the hints page for 298, where I kind of give you some hints right away in here on how to get started with that. We haven't defined the power spectral density yet, but we're going to be getting to that here shortly for random processes. That's what this problem involves. It's actually tied in with a sigma delta converter modeling. So back over to where we are here, we have, now we're going to finally simplify some things. I'm going to say, let's just assume we just have wide-sense stationary processes. We're not going to be so all-encompassing. Wide-sense stationary means that the mean is a constant, the variance is a constant, and the autocorrelation and autocovariance are a function only of the time difference between where the samples are taken, and that's m. So if I was to go back up here to this picture, the m that I'm talking about would be the separation in here. So let me do it a different way. That would be m, and then the way to make that work over here would be, I should have been writing this as, get my pen to work. So I'd be saying I was sampling at n, I'm sampling at n plus m, so the difference between the samples that I'm taking vertically down through the ensemble is m. And what I could do if I was in class, I'll try to show this on the camera, but that's not being recorded. If you take the separation between where these vertical sample, where this ensemble is being sampled, m is the controlling parameter that we see for a wide-sense stationary process. And in general, the behavior of a wide-sense stationary process would be it becomes more correlated as m gets closer to 0. So as the two vertical slices are almost on top of each other, there's a strong statistical coupling between the two vertical slices. As m gets bigger, they tend to be more or less unrelated. They tend to become uncorrelated as m gets large. A big exception to that would be if the processes have a periodicity to them, and that's called a cyclostationary property, where there's a period, a periodicity. So if it was a cyclostationary process, it would periodically get strongly correlated and then get weakly correlated in between and then come back again. But for excluding cyclostationary processes, ones that have periods, then they just fade away. Now in digital communications waveforms, that's where the difference comes in. The noise in a digital comm receiver would be wide-sense stationary, and then the comm signal itself would usually be cyclostationary because there's a periodicity associated with it. There's a clock that's running to form the data bits that are being transmitted, and that forms a cyclostationary relationship on the waveform. Not a big deal for us at all right here. Okay, so that blue box is a blue box because it has the important properties in it for wide-sense stationary, and autocovariance is just the autocorrelation at m minus the squared mean at x, and that this simplifies to mx magnitude squared, because if the mean is a constant, then if we go to this definition up here, we have the same value for each one of these, we just have the conjugate. So that's why it becomes magnitude squared. I'm about at the halfway point, so I could take a break. If you're watching this, and nobody is signed into Zoom as far as I know right now, but I'm going to keep it running since my computer is not struggling mightily. I'm going to stand up and stretch a little bit and maybe walk away from the camera for a moment, but I'm just going to keep barreling on through so we can get this done. So I've got my headset on so I can talk and walk at the same time. I can see the snow is still falling, lots of snow in my backyard. I have a bird bath that I'm looking at, and it looks like it's got about, I don't know, maybe 9 inches of snow on the top of it. It looks like a big white cylinder of snow sitting on top of it. And the trees are loaded with snow right now too. I have ponderosa trees that the branches are hanging down low with snow on them. So in the future, when you watch this and the sun is back out again, you'll say, this was that day of a heavy snow early in November. Okay, I'm sitting back down again. So let's carry on with the random processes. We're going to make some nice simplifications, though, because of the fact that we've got wide sense stationary. So we're going to introduce 2 different processes now, cross-correlation between jointly wide sense stationary, using the idea of wide sense stationary and extending it to jointly wide sense stationary will mean that the cross correlation, which is the autocorrelation when you have x and y rather than just x and x or y and y, is a function of just the time difference between the vertical slices of the ensemble for the x process and the y process. So that becomes a constant. And then the cross covariance works out the same way for the covariance. If we have, I'm looking at this bullet right now, if we have processes that are uncorrelated, and I'm going to get back to the idea of signal and noise at the input to a processing system, then the cross-correlation between x and y will just be the product of the means of those 2 processes. And if one of those is 0, which it generally is in a noise scenario, then we can simplify this cross-correlation to being just 0. And that's the assumption we'll be using in scenarios that we have coming up here. We'll be able to say that the 2 processes are uncorrelated, so there is no coupled term. There's no cross-correlation term that's non-zero. Okay, moving into the next big topic and kind of the final topic here of random processes is power spectral density. We've looked at properties of the autocorrelation itself. We looked at properties of the random process itself. We talked about autocorrelation, autocovariance, and then we talked about when you have 2 processes, we have an autocovariant, or we have a covariance, or cross-correlation, getting things confused myself. What about working in the frequency domain? Well, there's a very interesting relationship between the frequency domain and the correlation domain. The power spectral density of a random process is, in fact, just the Fourier transform of the autocorrelation. So assuming a wide sense stationary process, the autocorrelation is only a function of the time difference between the slices in the ensemble. The autocorrelation will just involve Fourier transforming this function phi xx of m, and that then produces phi x or pxx, power for power spectral density. Now, power spectral density is not the same as just the Fourier transform of the underlying process, but if you Fourier transform a random process, you get another random process in the frequency domain. If you're talking about the power spectral density, you're talking about a deterministic function for the autocorrelation function. And when you Fourier transform that, that's a deterministic function in the frequency domain known as the power spectral density. So that gives us a deterministic function to describe the frequency distribution of our random process. Inverse transforming the power spectral density gets us back to the autocorrelation function domain, and we can also interpret that the mean square value, which is expected value of the magnitude of x of n in case it's complex squared, is just phi xx at 0. That's the autocorrelation function at 0 lag. And lag is a term that's used to describe wide-chain stationary processes, and the value m, the lag is the offset between the two vertical slices we're talking about. The lag can be positive or negative, but if it's 0, that says it's on top of itself, and that is equal to the power spectral density integrated, because in this definition of the inverse Fourier transform, if you put in m is equal to 0, this term goes away. That term becomes 1 is what I meant to write. So that gives us a really important property that says integrating the power spectral density, we can get back the power in the random process. And for the special case of a zero mean process, or considering the autocovariance, the variance or the power in our signal x is just going to be the autocovariance, which is going to be integrating autocovariance at 0, which is integrating the power spectral density and subtracting the squared mean. But if we have a zero mean process, then that's going to be 0, and so we can get the power by integrating the power spectral density. So that's it for the statistical, probabilistically related definitions of a random process and things you can do with it to represent signals and operating. We're going to be passing these signals through systems here momentarily, but take a little side trip into looking at time averages. Time averages is what we end up doing when we're in the measurement world, whether it be on our computer when we create a simulation, or whether you're in the lab using an instrument to take a measurement. So the mathematics and the statistical side we've just come through, it gets pretty intense and pretty detailed, but we want to be practical as engineers and building systems where we use random process ideas to model and understand how things are going to operate. But then when we actually build the systems, we want to be able to take measurements and see that things are happening in the way we're expecting. So that's where the time average idea comes in. So we can define the time average mean as just simply running the mean over all of these samples of our process. And the time average mean, by its very nature, we're now going to interpret this x of n as just being one sample function. So one sample function. I didn't really point this out, but the idea of the random process and all of its infinite number of sample functions in the ensemble is just saying these are the possibilities that we have out there. When we're actually running our system at any given moment, there's a sample function that's going through that system, and it's the only sample function that it's going to be dealing with. We're just considering in our modeling, though, all the possibilities that are out there, just like if you're considering a random sequence of binary digits in a comlink, how many different sample functions are there? There's an infinite number because there's many different bit patterns that are going to be sent at random. But when we consider the operation of the system at any given moment, it's one sample function. So here we have the time average mean over one sample function, and these square brackets, angle brackets, are to denote time average, whereas the expectation operator is what we were just coming through, is works on the vertical part of the sample function, or the ensemble. So that's just taking one sample function, one vertical slice of the ensemble with the expectation operator, and the time average operator is working horizontally by working with just one sample function of the ensemble from minus to plus infinity. Or in this example here, it's going to be a window that's going to go minus L to plus L, but that window is going to expand to minus to plus infinity. We can also define the autocorrelation function in a like fashion using the one sample function and lags of the sample function, summing the products, and then normalizing by the number of sample functions we're utilizing. I mean the number of samples in the sample function we're utilizing, just like up here in the mean, the same idea. So to go further with this idea of being able to take measurements of systems we designed using random process theory, we would like to replace ensemble averages. And ensemble averages are, that's the ensemble average, and this is the time average. We'd like to be able to interchange those two. When we develop and model things, we'd like to be able to view things in terms of the ensemble averages, and then when we take measurements on our system, we'd like to be able to do the time averages. So we'd like to be able to have a relationship between ensemble averages with corresponding time averages that are using a single sample function. So this comes down to ergodic theory in random processes, which is getting even more intense sounding. Ergodic theory has got a lot to it as well. You can have a process that's mean ergodic. You can have a process that obeys correlation ergodic properties, and what those mean is that statistical mean and time average mean are equivalent for these two types of processes. When I used to teach random process theory all the time, that was back in the beginning of my teaching at UCCS, I taught a class in random processes, which was probability, random variables, and random processes for an entire semester. And this was covered in more detail and detailed mathematical proofs of some of these things, but this gets very, very intense. Keeping at a high level of abstraction and just thinking of, if this exists for the processes of interest to us, then we have a nice situation on our hands. We can do ensemble averages or we can do time averages, and we can assume that under approximations at least, since a time average can't average truly from minus to plus infinity, and an ensemble average theoretically can take the entire ensemble in one vertical slice and treat all of its possibilities, just because we have a probability density function to do that. We can still get near equivalence. So the idea here, and this is the way the book rolls, is that we can interchange statistical or ensemble averages with time averages. So the next little bit is just saying that it's not possible that L go to infinity, so on the computer we can just generate a long enough time average and work with that. It turns out when I have taught random processes, I use the computer, I use Python, MATLAB, whatever, to generate an ensemble, a finite dimensional ensemble. So you can do that with a matrix. If you think about it, you can have the rows of the matrix be the sample functions themselves, and then each row is another sample function, and then you can slice down vertically through the matrix to get means and variances, and then get coupling between various columns, and then you can get covariances and other things from that view of the matrix. And that is generally made for a nice project problem. It's not something we're doing in this class, but just letting you know that you can do that. And I probably have that in a project problem for let's just diverge here for a quick moment. If we were to go look at the website and back out of here and go to Communication Systems 2 This course starts off with random variables in Chapter 2. Or no, wait, probability in Chapter 2, random variables in Chapter 3. In Chapter 4 is random process. So this does continuous time random processes, but all of these ideas are in this chapter of what we've been going through, power spectral density, and so on and so forth. More detail on that, and like I said, I'm pretty sure there's a project or a homework problem that does some of these things for random processes on the computer. There's other classes that I taught, statistical signal processing. I'm not sure if I'm going to be reposting that content, but that has the most in-depth material on random processes. But then I have way back when, like I said, the course I used to teach entirely on random, or probably random variable and random processes for a whole semester. That has the most of all the things that I ever was doing routinely in class. Just like everything that seems to be going on, we tend to get busier and busier, and we tend to abstract, so we don't spend as much time on any one topic. We end up covering high level and then drill down as needed. And for all of you that are graduate students, this is what you do as a graduate student. You drill down more into specific aspects of randomness in the problems you're solving, to understand what's going on and how to develop improved algorithms to get better performance. So here's an example of an estimator for the autocorrelation that's finite in length, and it just uses finite records. So you can think of how this would work if I was to draw a picture over here and then draw another picture of the same record of data. You're essentially sliding these two records of data by an offset m, and then you're going to form the sum of products where it overlaps and divide by L. You can see that if that length is L, the overlap is going to be less than L as m gets greater than 0. So you will have a biasing when you divide by 1 over L in general. Now that seems like a bad estimator, but it turns out it's actually it's a better estimator in some ways than if you normalize properly. And normalizing properly means that you have to divide by L and multiply by L minus the absolute value of m, the biased estimator, or the unbiased estimator, so that you can relate the two. There's different types of estimators out there for the autocorrelation, and of course the statistical mean, or the time average mean. But needless to say, these things can be done, and you can use whichever are appropriate for your needs at the time. We have standard estimators for the covariance of a random process, and it's autocorrelation if you want to do that. They're all out there. We're not really using those in this class very much. We're typically going to go over to the frequency domain side and use the power spectral density and estimate it directly using FFT methods and averaging. I'll maybe explain that later, next week or sometime. Okay, the final topic in the random processes is passing them through systems. So when you have a random process, or a deterministic process for that matter, we have a linear time invariant system, so we can use the convolution sum to get the output from the input. My throat keeps getting dry, so I keep drinking my hot tea that I've got sitting here. If the input is a random process, so if this is indeed now a random process and we have our deterministic impulse response, we can go ahead and find the mean of the output by just operating with our expectation operator outside, and then it's a linear operator. I've talked about that already. We can bring it all the way to the inside. It's looking for the randomness in this problem, so it hovers around x of n minus m. If it's a wide-sense stationary process, this is just mx. Pull that out front over here, and then we see that the mean of the output is the mean of the input times what? The sum of the impulse response, but that is really just h of e to the j0, or the DC gain of our system. That makes sense, right? Input, the constant part of the input, its mean value comes out multiplied by the gain at DC of the system. So that's an easy one. We can also go after the autocorrelation function at the output in terms of the input, and that is more complicated. So just to be quick about it, you can show that it's going to be the autocorrelation of the input convolved with the time reversed impulse response convolved with the time response. Now, if you just want to think, why does the impulse response show up twice in here? It's because each y in this phi yy is involving a convolution of x with the impulse response. So that's where that's coming from. Alternately, we can write this phi yy as a convolution of phi xx with a new function, which is really just convolving those two together. And since h is deterministic, this is called the autocorrelation sequence corresponding to the impulse response itself. And we're going to see an example here pretty quickly where we're wondering, what does C sub L, how do we calculate C sub L? Well, or C of L, the autocorrelation sequence of the impulse response. Doing a convolution in the time domain is always an option, but it turns out because we have the Z transform available to us, we can switch over and use the Z transform, and we can use theorems from the Z transform, and that's what I've got going on here. This was a theorem we went through back in chapter 3 on Z transforms. If we time reverse a sequence in the Z domain, it becomes h of 1 over Z. And you remember what goes along with that is that the region of convergence goes inside out. So if the region of convergence was something greater than a pole radius, it would now become the inside of that, inside that pole radius. And if it's an annular region, it becomes an annular region that reflects 1 over the radii involved in the original sequence. So we'll go through an example of that here, like I said, shortly. We'll see how that comes into play. So this is probably the best way to analytically go through and get at the autocorrelation function of the output from the input and the impulse response. And the example that I have upcoming will demonstrate that. Another way of getting at it, though, is through the Fourier transform. And this takes advantage of this blue box result saying that the spectrum at the output of a system is just it's kind of messing up here, but You take the autocorrelation function at the input and multiply it by the magnitude squared of the frequency response, and that is the spectrum at the output. This is huge in terms of significance in modeling and in general common signal processing systems. So all we need to do is just multiply by the magnitude squared of the frequency response. So another way of getting at the impulse or getting at the autocorrelation at the output would be to take it to the frequency domain and then inverse Fourier transform it. And I think in my hints for problem set 5, trying to find the right page that I was on. When you work problem 298 and you get to part C, you can use this exact result, and it's easier to just inverse Fourier transform power spectral density to get to the autocorrelation function. So just bear that in mind. You've been good at figuring these things out in the past. In Chapter 2, everybody really liked using the Fourier transform to get back to the to make it easier to solve a problem. So that holds true here as well. If I'm coughing more, it's because my throat is getting more obstinate. I'm going to keep going though, for the time being. If that shuts me down, I'll let you know by stopping. So there are some special random processes. Probably the most famous one that we care about right now is white noise. White noise is just saying that in the properties of the process that its mean value is equal to 0 and its autocorrelation is just the variance of the white noise process times delta of m. So it has a nice simple delta function for its autocorrelation, and if we take and find the Fourier transform of that delta, we're going to get a constant sigma sub w squared. So this is a good thing to think about or have in your memory bank, saying that if we have white noise, we have a truly flat spectrum, and the whiteness comes about by saying that white is light with all frequencies in it. So it's flat, and it's flat on the interval minus the plus pi, and that of course extends because discrete time signals are periodic, and its autocorrelation function is just a single delta function spike. I have a fairly long-winded and detailed example explained here in the notes in example 4.14. This was done originally in MATLAB, and I just left it in the notes this way because I handle that since using Python days. Right in here in the Jupyter Notebook. So the Jupyter Notebook starts off in this section called Uniform and Gaussian Noise. This is pretty much paralleling what's going on here in the notes, where we've got generating white noise that's either Gaussian distributed or uniformly distributed. I'm just going to follow the MATLAB version since right now it's a little bit easier for me to look at it rather than having to run everything in Python. The same results are produced by this notebook that we were just looking at though. So the way this example starts out is it says, let's produce some Gaussian noise using rand n. That's what we can do in Python. Generate some uniformly distributed noise. In here, what's going on though is in order to make the variances be equal so that our looking at the power spectral density should be equivalent with either being uniform or Gaussian, is we have to make the variances equal. So here, that's equal to 1. We want to make our uniform have a variance of 1, so how can we do that? We know that sigma uniform squared is delta squared over 12. So what I'm doing in this example is I'm taking uniform random numbers that run from 0 to 1, multiplying by 2, and then I'm going to subtract 1, so that's going to make it be uniform on minus 1 to 1, and then I'm going to multiply it times square root of 3. So that's going to become, down here, uniform from minus square root of 3 to plus square root of 3. And so our delta is going to be 2 times the square root of 3 squared for delta squared divided by 12. And so that's going to be 4 times 3 over 12, which equals 1. So that's just proving to you that in this particular case, sigma u squared is equal to 1 for this second form. So I just did some plots. Those are connecting the dots on the waveform. If you look at this carefully, you can see that the extremes of the Gaussian are greater than the extremes of the uniform, because the uniform is just bounded between minus square root of 3 and plus square root of 3, whereas the Gaussian is going to be running from minus to plus infinity, or the numerical precision of the double precision numbers. If we drop down into here, though, and want to compare the autocorrelation function estimates between the two, we have an X-core function available in MATLAB and in Python. I'm trying to remember, did I have that in the notebook here? I have a function in the digital communications library package called X-core, which is very similar to MATLAB's, and I can get my autocorrelation functions from that if I want to plot them. Or actually, SciPy Signal has an X-core function too. I'm not sure I'm not going to take the time to fumble with the Python right now, since I can demonstrate that at another time in class. I can demonstrate and have you look. I think all I wanted to do, if I could get it to come up, but I don't know if I can. There we go. In the signal library, and what I'm looking for is what is the autocorrelation function. And I think what you've got available is correlate. So full discrete linear cross correlation of inputs, and the inputs are 1 and 2. So this is very similar to X-core in MATLAB. The X-core function that I wrote for Python, digital com package X-core, uses the FFT, and it has a different normalization. So that's why I'm not wanting to go down that path and get confused. The bottom line, though, is that we're looking to see in both cases that if it's, whether it's Gaussian or whether it's uniform, it's going to be sigma squared times delta of m and we define the random processes so that that's 1 in both cases. So I'm going to do an unbiased estimator, which I think is what Python uses also. This is the autocorrelation function. It approximates as a delta function of unity height approximately, and some fluctuations around 0. And this is the white noise. Same idea. So we're seeing we look good there. If we want to get at the power spectral density, in MATLAB we have P. Welch is available, and Welch's method is what I favor of using in PSD estimates in Python. So what I'm using to get the power spectral density down here, let me see, do I have a PSD example? I don't. So what I favor using now, and what we're going to be using in the other part of the homework problem, is here you're going to be getting at I guess you don't do power spectral density in here either. I'm getting myself confused. I'm thinking of the midterm, exam number 2. I'm just looking in the hints I have. I don't have anything with power spectral density in here. So if you're curious and want to compare, say, this power spectral density from MATLAB to what we have, what we can do in Python, we would be wanting to use, my preference is to use my PSD, which is just something that I wrote quickly, but now I'm leaving it in the package. I can put my signal in here, and then I can decide on what the FFT resolution is I want, and then I get back out of here the power spectrum estimate and F at the same time. So let's just take a quick look at that. It's power, so it's now going to be 10 times the log of 10, since we're in the power domain. Whoops, it's not x though, it's got to be x1. I'm trying to remember back to what I defined up here. Or it could be, in this definition, I'm just going to go with I don't want to try to pull this all together right now. What did I have way up here? I had x1 is 100,000 samples. It's not the same height, but it's going to be the right characterization. This is obviously a signal that has sinusoids in it, so it's going to be x1 in there. And if that looks too noisy, it's because we're plotting it zoomed in. So I could say y lim there. The vertical height has not been scaled in the same units I have in MATLAB, but you can see that it's flat due to the modeling here. I think where I'm off is that the variance on this is not unity. So and now it's too high. I divided by variance of x1, but the normalization that I have going on in this my PSD is not quite calibrated to be watts per hertz. But you can just see that I've scaled it up, though. I don't want to get bogged down into that right now either. So this, we see that they are the same in this particular example, because I was careful to get everything normalized properly for white or Gaussian. And now we're going to go through and send our signal through a first-order low-pass filter, and it's a low-pass filter of this form. It has unity DC gain. And now we want to analytically model, and this shows up in the second homework problem of set 5. We've got this sort of a filter, and we want to find out what this autocorrelation between the impulse responses is. That's what the CL function is. So we need to dig in and say, what is the CL if this is our H of Z? And so I say, let's find it using the inverse Z transform. So first we have to pull together H of Z and H of Z to the minus 1, and that's written out right here. And then we have to recognize that for A being magnitude less than 1, the region of convergence is magnitude of Z greater than magnitude of A. That's for the causal part of our system, and this is anti-causal because it's got the signal flipped and running backwards. That will be magnitude of Z less than magnitude of 1 over A. So we have an annular region. We have two poles, and we use partial fraction expansion on this, and we have two coefficients to solve for. Those are down below here, and then we can take these coefficients, build up our two sequences, the right-sided and the left-sided, and it becomes the two-sided exponential. And you had this in a homework problem back in the Z-transform chapter. That would be chapter 3. So this is a very notable result for a first-order system. It's kind of like a given. I've worked it for you. You don't have to reinvent the wheel on it. If you have anything that's a first-order system and you need the autocorrelation function, or you come at this from the power spectral density, you can use this property right here. And here it is, just comparing it between the theory, which is the dashed line, and the approximation done using the autocorrelation function of the output. They do match up. So the action of the filtering, what it's doing is it's taking the delta function of the white noise process at the input, and it's spreading it out because of the memory that the low-pass filter has. In the power spectral density domain, it's just multiplying the spectrum of the white noise times the magnitude squared of the low-pass filter's frequency response, and that's done right here, and we see that it tracks out as well. The reason why the estimate is so noisy is because I'm only using 4096 samples, and in the averaging of the PSD, I've only broken that down into 16 sub-records. I can talk more about that later, but I'm not going to get into the details right now, but it's following the trend at least. This example does go into the cross correlation. I'm going to, for now, skip over that. You can read about it. It does also hold. So now what I want to do is, as we head towards the end of the lecture today, I want to start getting into the application side of all these things to our problem at hand. So Chapter 4 moves along into digital signal processing of analog signals. So this is where we're going to develop models for the continuous to discrete and discrete to continuous processing blocks in more detail than what we've had so far. So we're going to have, we're going to consider quantization of the analog input in particular, and this is where we need the random process theory. So what I've just come through is to immediately be able to use it in this context. We're also going to be talking about anti-aliasing filters, which we haven't really talked about. That's another linear operation now that we just need to make sure we don't have aliasing issues. So the top diagram, this is the so far we've been in the class. We've been considering this for analog input and output, and now we're going to zoom in on elements inside of there and say that we have to have an anti-aliasing filter. So we have to add this in. Pencil is not working well for me. We have to add in a model for the sample and hold, and then we'll have more or less an ideal A to D at that point. And then we have to model the reconstruction operation out of the back end. So pre-filtering to avoid aliasing. This shows up in the very last homework problem of set number 5. It's a bonus problem, so you don't have to work it, but the idea here is that in order to protect ourselves from having aliasing, we need to put some anti-aliasing filter into our system. An ideal anti-aliasing filter is what we want to have, but we can't ever have that. So we have an approximation. So that's where the homework problem comes in. It's wanting to consider how you can equalize things when you have an imperfect anti-aliasing filter. So this points out the fact that we can only approximate our anti-aliasing filter, and in fact, no time-limited signal is strictly band-limited, and we can't make our filter band-limited. So in general, we're going to have to settle for the minimum attenuation of the alias signal and or the noise components that are writing in on the input. So that's where this comes in to play. It says that we get the signal of interest pumped through our effective frequency response to the output, but then we get two other components. We get some alias signal components leaking in, and we get some noise that's folding down due to aliasing and landing on top of our desired signal and noise. So fundamentally, that's just the way it is, but there are things we can do to make it easier. So we can do multi-rate sampling, and we'll talk about sigma delta later, not in this lecture, but we'll probably hit that the very first part of next week. By using multi-rate sampling, though, we can make it easier to build a filter and get closer to true perfection. So the idea is we want to avoid having a sharp cutoff analog filter and instead move that sharp cutoff filter inside of our DSP system. So here's how the system works. We have a low order anti-aliasing filter up front, something that's easy to make. We don't have to worry about having distortion in the passband of interest, 0 to the Nyquist rate. The filter can roll off faster, but it's going to happen further up in frequency. And then our continuous to discrete converter has to run at this oversampled rate, and the oversampling rate is M. So that is an expense. We have to have an A/D that can run at a higher rate. We have to be able to process samples faster initially, but polyphase filtering can come to our rescue if we want to deal with that. This is the rest of the block diagram. This right here is an ideal candidate for a polyphase filter. But for keeping things simple, I'm just simply going to say a high cutoff filter running at the oversampled rate and then downsample. But polyphase can do this for us. That was stuff we talked about last week. So the analog domain filter can roll off gradually, and then we can clean things up in the discrete time domain. And this is the verbiage in the bullets. So this I've already talked about. Additional processing is a trade for more difficult, expensive analog filter design. It's generally worth it, though. So this is a pictorial based on an example that's in the book to just say that, okay, our signal of interest is right here, but we also have some high-frequency noise present that's probably inside our signal of interest, but it also extends beyond the signal of interest. I'm thinking of audio now, where things beyond our human hearing are still present in our environment, and we don't want to be processing them, but they are out there. So what you do is you come in with your anti-aliasing filter to be flat, not really trying to do anything right up against this omega sub n. Instead, you have it start to roll off gradually down to some cutoff frequency. And this is the signal that's going to be oversampled. So your anti-aliasing filter provides some attenuation of the high-frequency noise and unwanted signal. I'm sorry, I'm touching my mouse, and I just have to touch it, and it zooms away like that. And then what you want to do is have your high-order decimation low-pass filter come inside once you've got things converted to digital, and then you can fine-tune the shape of your spectrum and reject the folded over alias noise and so on that's outside your band of interest, and then finally this is what you get. This is the key point here is that we pushed the requirement of the anti-aliasing filter into the digital domain. We have to sample at a higher rate, but we can use a polyphase filter, and then we can get things cleaned up nicely. The sigma delta converter that we're headed towards, I'll talk about that next week, takes this even further. It does exactly this. It will sample at maybe 64 times in an analog, or an audio application chip. And then not only that, it doesn't have to require, say, a full 16-bit conversion. It can do it with 1 bit. And that's the amazing part about the sigma delta. It can be a 1-bit converter, oversamples at a high rate, and you end up with a very nice output at that point. I've got it here in the notes, a discussion on general anti-aliasing filter design. This is based on a Butterworth shape. It kind of repeats, but from a more practical standpoint, what we just went through, and it comes up with an example that at the very end is just saying that for this particular shape of the signal of interest and the need to band limit it to a certain dB level to avoid aliasing, a 17th order Butterworth is needed initially, but if you're willing to sample at 4 times the sample rate, you can get by with a first order Butterworth and then just have a high order low pass and a downsample by 4. So this is just kind of a dramatization of what we just went through. So in the example I go through here, I'm saying we're going to, instead of sampling at 1 megahertz, we're going to sample at 4 megahertz, but this analog filter can be much, much simpler And then in the DSP domain is where the fine filtering is done. Okay, keep my eye on the watch. Got 20 minutes left. The first part of our signal chain is to look at the impact of a sample and hold on it in front of an A to D converter. Most traditional A to Ds need to hold the signal with some analog circuitry so that a physically realizable A to D has a stable signal to look at in order to go through its conversion cycle. So what does the sample and hold look like? It's an impulse response that has a rectangular shape in the analog domain, which would be a sinc function in the frequency domain. In terms of the waveform, what it looks like is this. It will take the input waveform, and it will take, at each sampling instant, stretch the signal out and hold it as a constant. What does this do inside of our system as a result of the zero-order hold? Well, it's important for the operation of the A to D to have, perhaps, in some instances, the zero-order hold. But the important thing is that it doesn't really alter the samples that we capture into our discrete time system. Now, there are issues with the sample order, zero-order hold, or the sample and hold, such as jitter and other things that can get in. But those are far more detailed than what I care to go into or the book cares to go into. So we get really no impact. Ideal sampling can still occur. The next step in the A to D process, though, is that we have samples and we're going to convert them to finite length digital words. So we're going to go through a two-step process. This is a refinement of the previous model. We've taken the zero-order hold out. We've got it to the discrete time domain, but we don't really have our hands on this because this is something we can't actually touch in a real system. We have to now represent it as a digital word. So we have a quantizer, and then we code the quantizer output. And it's a two-step process, but again, we're just going to abstract it into a one-step process. The one-step process is this, just saying we're going to quantize our signal. And how do we quantize? Generally, the quantizations are uniformly spaced, but for speech, it was learned a long time ago, in telephony at least, that you'd want to use a non-uniform quantizer to get the best voice quality, and this is something Bell Labs learned about a long time ago when they went to a digital telephone system. I'm not talking about the digital cellular telephony. I'm talking about wired telephony that was done digitally after it left the switching center in your neighborhood. All those things are kind of irrelevant now because most of us use our cell phones for everything. But in the cell phone, something also has to happen there too. So what is the operation of quantization? For signed amplitude values, which is the easiest one to talk about and the one that's most relevant for the modeling we do in this class, we're talking about a rounding quantizer, and that's what this picture is depicting. The fact that you have a stair step at 0 in your quantizer, and then you have a symmetrical set of stair steps on either side, except because we have a power of 2, this stair step corresponds to this one, and this one doesn't exist in the top half, and that's the very nature of signed arithmetic, and 2's complement reflects that fact in terms of the codes that you get moving from top to bottom. So everything that I say really refers to what is what's done today, and that's 2's complement. There was a form called offset binary that could also be used, or when you play and work with microcontrollers, sometimes your A to D on the microcontroller is a unipolar A to D. It only digitizes positive values, but we're talking about signed values quantizing, and that's where the 2's complement comes in. So you can represent that with a step size, which in the book is defined as xm over 2 to the b, and the book is very careful about the number of levels, is 2 to the b plus 1. So you always have this laying around. So if you have 16 bits, we have 2 to the 15th levels times 2. And this 2 in here represents the sign bit. So in people that talk about quantization would say if you're using 16-bit signed integers, you're working in Q15, which means you have 15 bits to the right of the binary point. So just remember that if I say a 16-bit converter, I mean B is equal to 15. And I know I'm quickly running out of time here, but let's just go back over and look at the assignment sheet again. So in this problem, which is the third problem, you've got a 24-bit A to D. So this has got 23 sign bits in it, 24 bits total. And then you're going to work through some modeling things in here. I'm just right on the top of that right at this moment. So I feel like I'm cruising in to the finish line here. And this is stuff you don't need for this Friday or next Wednesday. You just need to have it for next Friday. So back over to here. Just talking about the representation of the bits themselves. You've got a binary point, and this is the idea. This is the sign bit, and then these are the B bits that represent the magnitude. And then this happens to be just a formula that you can use for going from bits toggled on or off to represent an amplitude value that has a max value of xm. And the max value is cheated by one level on the positive side relative to the negative side. And that's why if we're working in the fractional part, we have this expression right here. We can go all the way down to -1, but we are just one quantization level less than 1 on the positive side. It's a little exercise with 2's complement. Okay, my finger did amazing things on my touch screen. They blew it up really big. So in terms of the example I was carrying on in here, going from -1 to almost +1, this is what it looks like in terms of the quantizer. The input comes in as a solid gray. It gets ideally sampled and held with a solid line, and then each of these solid hold values or held values by the A to D sample and hold then get quantized. So here I'm being really nitpicky, and I'm saying it looks like I'm at 1/2, so I'm quantizing up to the next highest level. I don't know, I drew this out by hand, and I don't remember if I took all the cases into account, but here it's looking like I'm quantizing the next level goes up or the level goes down. So you're creating error that's symmetrical about the nominal quantized values, and those are these values right here for this 4-bit quantizer. So there's, or 3-bit quantizer. There's 8 total values in here. So how do we model this? We model the quantizing operation very simplistically. Rather than the actual quantization, we want to model it mathematically on pencil and paper effectively, and we model it as an additive noise model. This is subject to argument, and it's based on a long-standing simplification, though, that you say to just model this, not run a simulation. We're just going to treat the output of the quantizer as if it's the true input plus additive noise. And this additive noise is uniformly distributed over the quantization step, half below and half above. So this is an application of using random variables, and then of course it's a random process because it's a sequence of values. So we've got uniform on this interval plus and minus delta. And although this is really simplistic, it does work quite well. So we assume that the error sequence is a stationary random process. We're assuming that these two are uncorrelated, which is very hard to justify because one's derived from the other. And then we assume that En is a white noise sequence, something we've already gone through, and that the PDF is uniform over the error signal range. So this ends up looking like what, just got a message saying, do I want to go to a brass rehearsal tonight? So I'll have to answer that here in a while. Assuming uniform over plus and minus delta over 2, and that's delta squared over 12 for the variance. We now have everything we need to come up with an approximation for signal power to quantization noise power, and that's what this homework problem does. So look at this problem. This code down below here is MATLAB syntax, but in Python it's the same thing unless you want to do a whole vector. So you have a different function called RND, which runs in MATLAB to round. At any rate, here I've done a signal, quantized it, set the number of bits I quantized to, and I then do a comparison. So with only 3 bits, here's the quantization, and just showing that there is a stair step when 3 bits are sent through. Here's the error signal. It does not look uniformly distributed. As a matter of fact, it looks very periodic. If I go up to 8 bits, it's looking more noise-like, but you can still discern that it has kind of a periodic looking nature. It's not really so clear anymore. And if you go up higher and higher, it becomes harder. If you go look at the histogram of the error sequence, you can see that as you go to 8-bit, it's becoming more uniform-like. It's not very uniform at 3, and it still works fairly well, and I'm going to be able to demonstrate that, perhaps not today, but this is our quick back-of-the-envelope calculation that lets us get the signal to quantization noise power ratio in dB. Variance of the signal power and variance of the noise power is what this is doing. So this calculation here is what you have to calculate for whatever your input happens to be. If it's a sinusoid that's getting quantized, this is just 1/2 a squared that you're familiar with for the power in the sinusoid. And then, of course, the sigma E squared is just based on the properties of the quantizer. This is controlled by B and XM. So you have to know what the number of bits are. Total bits is B plus 1 and XM, and that's, just flip back over to here. You can see delta is 2 to the minus B times XM. So you can get that calculation done, and then you know what delta is, and then you know what sigma E squared is. That is actually built into this equation already. You just need to know what XM is. You need to know what the standard deviation of your signal is, and here is where B shows up. So this does it in this second version right here. People will say that if you increase the number of bits for XM fixed, you increase the SNR, signal to quantization level. So I'm a little bit sloppy there. I said SNR, but a lot of times you put a subscript there, Q, to say it's SNRQ due to quantization. A little bit more discussion here on taking a normally distributed signal and quantizing it. This just shows us that if you want to set XM so that you don't exceed, your signal doesn't exceed the quantization level of plus and minus XM, that you end up having to back the signal off a little bit, and you net out a signal to quantization level of about 91.3 dB. Probably better to call that Q again. So the next thing is D to A conversion. Let me just, as I'm getting ready to wrap up here, let me just flip over to Jupyter since I've got this in here. So I have a nice function inside SIGSYS called simple quant, and this allows you to do quantization directly. You can just calculate out the quantization by just simply putting in the waveform, how many total bits you want, and then what the amplitude is of your quantizer. X max is this third value, and then what type of quantization you want to do. So here, I'm just running the equation that's in the book, I believe, 92.07, and here I have a simulation actually put together which is going to produce a sinusoid at some sampling rate, some frequency, and then also generate additive white Gaussian noise to simulate quantization noise, and then also quantize the signal to 14 bits. So now I've got that sitting in here so we can see what the help looks like. B total is the second argument, X max, and then what type of limiting you want to do, whether you want it to be saturation, overflow, or none. Generally, I will take saturation, but overflow is useful because it models the two's complement overflow characteristic, where a positive number overflows to a negative number and so on. So, like I said, I'm just about out of time, so I'm just running this because I don't remember exactly what all I've got in here. So here's the noise model. Here's the actual. I know I've got something else that goes on with this. I will want to spend more time on this for sure later. But just to get you a little idea as I'm fading out here, the time is going quickly. Let's just do a quick little, let's just go with 100 samples. $20 samples per. Whoops. Notice how Python, how the notebook picks up the fact I didn't close that off properly. So XQ, hit tab here, I'll get simple quant, pick it, I'll put my X in, and I put in 8 bits, set at X max equal to 1.2, so I know I'm not going to have any overflow issues, and then I'm going to put, for my limit, I'm going to put overflow. Which for some reason or another I'm forgetting if it's the full word or not. Nope, it's not overflow. Oh, okay. It's over. Okay, I knew it was an abbreviation. I just didn't remember for sure. Okay, so there it is. And now I can go ahead and I can just plot N and XQ and to better see the quantization, I think it's stairs. Either that or it's stair. I don't remember for sure. It's drifting off right now, so it's not doing it. What I was trying to do is what I need to do is go up to 1,000 in here. Just use plot and let it do what it's supposed to do automatically. Okay, so now what I'm going to do is I'm going to purposefully take this down to, say, 4. And now you can see that it is indeed quantizing. And now the disastrous thing that will happen if I only make this be 0.08, now we're getting the overflow, so it's becoming negative rather than positive. And if I even took this back up to, say, 10 bits right in here, we're still getting the overflow, which is not at all good. It's very disastrous. If I was to set this at 0.95, we'll still see the overflow occurring in there. Whereas if I was to just set it at saturation, what it's going to do is it's going to clip, which isn't nearly as chaotic as the overflow is. And if I put in, I guess it's none, it just merely goes about its way and says, well, I'm just going to do it anyway. I'm just going to let it go through. Okay, a lot to be thinking about here. Just going back to our homework problem, these are the things that we were just going through. You get to test that out, and then you do some more analysis right in here. This is not really a simulation-based problem. This is just simply analysis based on what we were just modeling from the lecture notes. Problem 10 is a bonus problem involving a compensator for an anti-aliasing filter, and this is done. Actually, it's for a D to A, so it's for a compensating filter there. I'll have to pick that up next week when we come back. Thanks for being patient and waiting for this, since it's going to take me a while to process this video and get it out there. I'm going to stop my recording right now, and then I'm going to shut my Zoom down and see if anybody's been listening. Bye for now.